prior to that, I am going to discuss again the same point which Professor Sangle has covered briefly, very briefly, maybe 5-10 minutes or 15 minutes I will take for brushing up the basics of the Prestressed concrete, and then we will go with the use of software in considering the analysis and design of Prestressed concrete beam and slab. My entire presentation, I think, can you see the screen now?
Sir, you just go into the PPT mode,
Yeah,
PowerPoint
correct.
presentation.
Can we go to that? Yeah. I think now you can see the whole screen.
Yes, sir. Yeah.
Yeah. Now I am going to cover the following topics briefly. That is introduction about the Prestressed concrete, basic theory of Prestressed concrete, codes of practice that we use, then materials that are going into the Prestressed concrete, permissible stresses for different materials, then important characteristics of Prestressed concrete, that is loss in prestress, and anchorage zone stresses at the end, the difference in design philosophy of RCC, steel, and Prestressed concrete, because you have studied RCC design, the design of steel structure, and now you are studying Prestressed concrete. The basic difference in the design of these three materials, we will have a look at that. And then we will go for softwares for PT design, the software-based design of PT beam, and software-based design of PT slab with concluding remarks. Okay. Now let us consider the Prestressed concrete. So basically Prestressed concrete, as you all know, that it is a concrete in which there have been introduced internal stresses of such magnitude and distribution that the stresses resulting from given external loading are counteracted to a desired level, which means you have got a structure, maybe a slab or a beam. When loaded, it develops certain types of stresses, bending stresses, say tension at one place, compression at the other. Now, in prestressed concrete, we introduce opposite types of stresses in those fibers, so that if initially you want to counteract the action of the load, then you expect that eventually there will be tension in the bottom fiber and compression in the top fiber. So you introduce the prestress force in such a way that it induces tension in top fiber and compression in bottom fiber. Once that is done, then you apply the load, and these tensile forces developed in the top fiber get reduced, or they might become compressive also. And in the bottom fiber, we will have the initial compression reduced to tension, or maybe small amount of compression, and so on and so forth. The reason for using this technology is that concrete is very weak, as you know, in tension. So as soon as you apply loads, with a very small amount of load also, the concrete starts cracking, and the tensile strength of concrete being very low, we are effectively using only that part of the cross section which is in compression, and a huge part below the neutral axis is of no use to us. Only the steel present in that area is of use to us. Okay. Now the applications are common, that is bridges and PT slabs, railway sleepers, the rail sleepers, electric poles, floor grid system, raft foundations, and so on. Wherever you have got bending moment or the tensile forces, then you can use Prestressed concrete. There are three basic theories for understanding the behavior of a Prestressed concrete member. One is the stress concept, where we work out the stresses due to the applied load, stresses due to the Prestressed concrete, combine the two stresses and see whether these stresses are within limit, and so on. So we apply this concentric force. There is a lateral load over here. This lateral load gives rise to bending stress. This direct force applied gives uniform compression. And then combining these two, we get this stress distribution over here. So this is basically the stress concept. There is another concept to understand the behavior of Prestressed concrete, and that is force concept, where we say that concrete which is in compression develops some compressive force at one end. There is a tensile force due to the tendon that you are, or prestressing cable that you have got. These two form a couple, and then we say that this couple is going to counteract the moment of the applied load over here. So we have got moment due to the internal forces, tension and compression, and the other one is due to the applied load. So the two are able to balance each other, and thereby we can control the behavior of the beam. The third one is the load balancing concept, where once you consider the cable as a curved cable, then the tendency of the cable is to straighten up, and in the process it develops an upward thrust internally. At this point, there is already a downward load over there, The result of that is you have got externally applied downward load, and you have got internal force which is developed by the tendon which tries to straighten up, push the girder in upward direction. That can be converted. The axial force in the cable is converted into this uniformly distributed upward load due to the profile of the cable. So these two loads act against each other, and the result of that is you have got this particular stresses due to the net force that you have applied, because you have got a downward load 45 kilonewton per meter and upward load due to the profile of the cable 35.3. The resulting force is now going to develop some moment in this particular way. There is a uniform stress due to the axial force in the cable, and then you get the net diagram in this fashion. Okay. Now this is as far as the basics of the pre-stressed concrete is concerned. Now when you compare the behavior of pre-stressed concrete and reinforced concrete, then we can say that as far as concrete is concerned, you can have low grade concrete, M20, M25, while for pre-stressed concrete you need high grade concrete, at least M35 and above. The steel reinforcement that you use is a mild steel Fe415 or Fe500 grade, that is the 0.2% proof stress of the steel, while for high tension strands that you use in pre-stressed concrete, the grade is 1800, that is 1800 Newton per mm square, as against 500 that you get for the conventional high yield strength deformed bar. Now, in normal concrete, the concrete cracking is acceptable. We say that below the neutral axis, if concrete cracks, we have no worry at all. We say that that is in any way neglected. While in case of pre-stressed concrete, the tension, cracking is controlled, and we don't allow a huge amount of tensile stresses there. The tensile stress is limited. Now the structure in normal concrete structure can be, or the members can be in compression or tension or flexure, like your column or beam or slab and so on. But for pre-stressed concrete, you need the member either in tension or in flexure. A member which is in compression, you cannot use pre-stress for that, because pre-stress adds to the compressive force. Thereby, a member which is in compression cannot be designed as a pre-stressed concrete. If it has got compression plus bending, then of course there might be tensile stresses develop, and to that extent you will be able to use the pre-stress concept over there. Now, as concrete beam can have any length, it can be even a 1 meter long beam, no problem with that. But with pre-stressed concrete, it is not possible. If the member is too short, say maybe 2 meter or 3 meter, then the losses in the pre-stress are so large, particularly the slip at the tension at the stretching end in jack, that the whole pre-stress will get vanished, because 2 to 3 millimeter is the slip that occurs during at the time of locking of the cable. So if your member is very short, then huge amount of force will be lost at the slippage, and thereby we will say that the advantage of pre-stress is completely lost. The reinforced concrete can be generally executed at site by unskilled labor, because very small amount of technology is required. While in case of pre-stressed concrete, you need highly technically skilled people, skilled labor is required to lay the cables, to stress the cable, to do the grouting, and so on and so forth. Very specialized equipments are required in reinforced concrete structure, maybe only a mixer and a vibrator and so on. While in case of pre-stressed concrete, specialized equipments are required, like the hardware for wedges or the cones. Then you have got the sheathing pipe which holds the cables. You have got the jack for stressing the cable, pumps for injecting grout inside the sheathing, and so on and so forth. And the last point is working cycle is of short duration as far as reinforced concrete is concerned. That is, you lay the reinforcement, pour the concrete, and then you start curing. After about 15-20 days, your concrete is ready to take the load. In case of pre-stressed concrete, the cycle takes more time, because you have to firstly lay the normal reinforced concrete reinforcement, then you have to lay the cables, then you have to do the concreting, which is okay, then you do the curing. Afterwards you have to do the stressing operations, so all the cables need to be stressed, and then you will have to do the grouting. So there are several activities involved. Thereby, if your normal slab can be done a cycle, that is one slab and then the next slab, if that takes about 2 weeks, With prestressed concrete, it may take 2.5 weeks or another 4 5 days will be required. So to that extent, the progress will get hampered, and so on and so forth. Now, course of practice, you have got standard Indian course of practice, that is 1343. Now it is revised in 2012. Exhaustive revision is there. In addition to that, you have got other country codes like ACI 318, BS 8110, and Eurocode EN 1992. So these codes are available whenever you have got any doubt or about the confirmation of your concept and so on. You can refer to these codes. As far as materials into prestressed concrete is concerned, we have got concrete, high strength steel wires, non-prestressed normal reinforcement is also required. Grout for bonded strands. Strands are of two types, either bonded or unbonded. If you have got bonded concept, then you have to do the grouting, so you require grout. Then you have got permissible stresses for different materials, and you need lots of hardware for prestressed concrete like wedges, sheathing, then stressing jacks, grouting pump, and so on and so forth. Now, as far as concrete stress strain relation, I think I will just rush through it. You all aware of that. Then you have to consider for concrete the stress strain relationship. Then you have got creep phenomenon to be considered, because creep also affects the behavior of prestressed concrete, because creep is the effect of sustained loading, and you have got large amount of load applied in terms of this prestressing force. So you need to consider the effect of creep in concrete. Effect of shrinkage also results into certain loss in concrete. For high strength steel wire that you are using, you are having a very simple stress strain curve over here. The strain is very small. The ultimate strain is to the extent of 4 to 5%, while for torch steel that we normally use, it is about 14.5% minimum, and for mild steel it is 23%. But for high strength wires that we use in prestressed concrete, the ultimate strain is about 4 to 5%. So it is very, you can say, brittle material. High strength steel wires have got these different diameters, right from 6.35, you can go up to 15.24, and for each of that the load is specified as to its load carrying capacity and so on. Now, relaxation is one phenomenon which you have to consider in prestressed concrete, because when you have got the high strength, high stress applied, say 1500 MPa and so on, due to this high stress that you apply, the internal molecular adjustment takes place, and over a period of time, the strain increases. The result of that is your stress decreases to some extent, and to that extent, you have to consider the loss in prestress due to relaxation of high strength steel. Now, for non-PT steel, we have got normal Fe415 or Fe500 grade. And for grout, it is a simple cement sand grout, which you use in such a way that the sheathing is completely filled with this material. The conduits are required for housing your PT strand in post-tension bonded prestressed concrete. In pre-tension, no conduits are required, because there is perfect bond between the strand and concrete, which is not there in post-tension. For bonded tendons, conduits are made of ferrous material or high density polyurethane. So plastic material is also used, and so on and so forth. So grout protects these PT strands from corrosion and so on. Now, this is some of the hardware which I just want you to have a look at that. Now, this is the multi-strand wedges, where several cables are stressed at one go. Now, these are flat wedges where in slabs we use side-by-side cables, and these cables can be either 2, 3, 4, up to 5, you can place them. This sheathing is also flat, and accordingly you need to pass these cables through the sheathing and carry out the stressing operation. While this is that HDP sheathing which I have indicated to you. So these days more and more people are using this rather than metallic sheathing over there. Then you have got single strand jack, which is used in mostly the slab prestress operation, where single cable is traced at a time. While this is a multi-strand jack, where several cables are traced simultaneously. And you have got this grouting system where the ingredients are mixed together along with water, and after mixing is complete, it is pumped and put into the sheathing and so on. So this is one particular layout of site where the cables are laid in both directions. You can have a look at that. These are flat sheathings where one or two cables are laid inside it. The cables are placed in both directions. You can see how the cable profile is maintained. So at this point near the support, your cable has to, I mean, stressing force has to resist negative moment. So there is tension at top. So at the support end, the cable is raised. At the midspan, you can see that it is lowered, and so on and so forth. So this follows the bending moment pattern in the given structure and so on. Now, permissible stresses in concrete and steel, I think I will skip this because you are all aware of that. So, as far as the permissible stresses are concerned in concrete, we have got permissible stress in compression, permissible stress in tension, and code gives several conditions under which these stresses are to be limited, and so on and so forth. The loss occurs in stress due to the elastic shortening of concrete, because when you apply compressive force due to one cable, so the length of concrete slab or beam gets reduced slightly, whatever it is. You stress next cable, it further reduces, and so on and so forth. With all these reduction in length, the pressurizing force of the earlier cables keeps on reducing. The result of that is you have got some loss in prestige. So if initially you had applied, let us say, 300 kilonewton of force, then eventually it may be reduced to 260 or 270 kilonewton, and so on. Then the creep of concrete over a period of time, concrete deforms, and with this deformation, the strain increases. The result of that is the pressurizing force reduces. Same thing happens with shrinkage of concrete, and when concrete contracts, it reduces the length of the tendon, and thereby the strain is reduced. Relaxation, I have indicated, due to the molecular adjustment, the stress gets reduced. Slip at anchorage, when you stress the cable and want to lock it, at that instant it slightly slips from the jack before it gets locked. So about 2 to 4 millimeter elongation is lost. To that extent, the pre-stress is lost. And then further, the bending of the member results into some change in length of the strand, which can increase the stress if it is on the tension side, or decrease it if it is on the compression side, and so on. Further, there is friction between the tendon and the sheathing inner wall. So that friction reduces the effective pre-stress to some extent. But most of the HDP sheathing that I have shown you, they have got very low coefficient of friction. So they reduce this loss due to friction, and so. I think anchor zone stresses we will skip it, because locally very high stresses are developed and some special reinforcement is required to be provided in the anchorage zone, and so on. Now we shall go to the main topic of interest to us, that is the softwares for PT design. So we have got various softwares available. Adapt, I think recently you were exposed to this Adapt software. It is one of the software which is used widely in industry. Over the years, this Computer Society of India, they have already had softwares like SAFE or ETABS, which were dealing with concrete and so on. Now they have brought out the SAFE software with Prestige option. ETABS also is now recently brought out with Prestige option. There is one software, RAM, which is from Bentley, which is also able to handle Prestige concrete design. And RACT is another software, which is Australian software, which also is used in industry. There are users for all these softwares, and the industry is flooded with several softwares in Prestige concrete. Okay. Now we will consider the basic difference in the three types of materials for which you have learned the design concept. Your steel design, for example. If you want to design a flexural member, say bending a beam for resisting the bending moment, then what we do is we select some section. Okay, ready-made section is there, say I section, channel section, built-up section, any section. It has got some section modulus ZB. So if there is some bending moment, design bending moment, then we divide it by ZB and say that, okay, now this is the actual stress. If this stress is within limit, then we say that, okay, my section is fine. If the permissible stress is 150 or say 165 Newton per mm square, my actual stress is 130, I will say, okay, fine. If it is 120, I will still say, okay, it is fine, because it is more less than the permissible. So we are okay. Now, if you need, for example, if you select and say ISMB 300 section with some section modulus, and later on you decide, oh no, I want more safety. So instead of ISMB 300, for same application, I will use ISMB 400. Doesn't matter. Nothing will happen to steel structure. It will be more safe, but nothing harmful about that. Same thing happens for concrete. Now you require some reinforcement in concrete. So you have got some bending moment divided by KD multiplied by stress in concrete, that is force over there, that is stress that will give you the area of reinforcement. Okay, I think I just missed this, but it is stress into the lever arm, so that will give us the reinforcement required. Suppose you require, let us say, 2000 square millimeter area of reinforcement, then you say that okay, I want to provide 2500, no problem, you can provide always more, and there is assurance that it is more safe and nothing happens. Only thing is, when you are using limit state method, then it might not be advisable every time to use large amount of steel, because that reduces the ductility of the structure. But otherwise, nothing is going to happen to the structure if you provide slightly more steel. But in prestressed concrete, I cannot say if I want to apply two cables, for example, and it is able to satisfy all my requirement. Then I cannot say that, to be on the safer side, oh, instead of two, you use four cables, and instead of applying 30 kilonewton for 30 ton force, why not apply 40 ton to be on the safer side? Oh, that's not correct. In prestressed concrete, you cannot go on the safer side in this way. This is going to make the structure unsafe. You need to provide only that force which is calculated and satisfies the constraint in terms of stresses, crack width, deflections, and so on. You cannot later on say that okay, instead of providing cables at 1 meter, let me provide cables at 700 millimeter itself to be on the safer side. That's not correct, because that will make the structure unsafe and so on. So in prestressed concrete, once you provide certain data, then that data is only to be used, and no one can change that data for making it more safe. It will be making it dangerous and so on. Okay, now let us consider the simple application of this software, ETABS software, which I think most of you are aware of as to how you are using this ETABS software over here. So in ETABS software, as you know that you need to follow certain steps for using this software for analysis purpose, design purpose, and so on. For that purpose, now I am considering a simple data. So I am considering a simple beam in this fashion. So this is a rectangular beam. 15 meter is the span of the beam. Can you see that? 15 meter. Okay. Now, the cross section that I have selected, if you see these letters, it is 400 by 900. So it is 400 wide, 900 deep. Now that's the beam I am considering. It is a simply supported beam over here, and it is subjected to a live load of 25 kilonewton per meter. Okay. So that is my data, that I want to design a beam which is 15 meter in span. The section I have selected is 400 by 900 depth, and it is simply supported at the ends. The grade of concrete that I want to use over here is M35, and so. Now I want to use the tendons in it. So for that purpose, now we will go back to ETABS and see how the tendons are considered. But in the present case, what I have done is I have proposed a two number of cables. I will indicate to you the area of each cable and so on. And this profile is generated by using the software itself. So I am able to get this profile of the cable. It being simply supported beam, there is no moment to be resisted at the end, while maximum moment is to be resisted at the midspan, and so on and so forth. So if I want to design this particular beam using prestressed concrete and check whether the number of cables that I have selected and the profile that I have considered and so on, whether it is as per my requirement or not. So I will now consider this ETABS software for that. Okay, so this is my ETABS software for that. Now for this particular beam, I have considered the 15-meter span. Now you can easily generate this particular span. Okay. I think you are all aware of generating a beam over there. Shall I take for granted that you can easily generate a beam over there? No need to teach that, or no need to explain that? Okay. Now, once you consider this beam, then for this beam, as you know that in ETABS, you need to consider two definitions. One, you need to consider the material property. Okay. Now you have considered the material property of only three materials. Say the concrete that you are considering, this is M35 concrete that I have considered with its modulus of elasticity accordingly adjusted 5000 root FCK. So I have taken this particular concrete of grade M35, and Okay, now that is my grade of concrete. As far as normal steel is concerned, it is Fe415. So I have considered Fe415 as a normal steel because I will have to design later on the stirrups for this. And also, though I am using prestressed concrete, I need to consider the moment resisted by prestressed concrete. Maybe 70% or 80% of the moment might be resisted by prestressed concrete, but remaining moment will have to be taken by non-PT steel. So for that purpose, I need to get the data for this non-PT steel M35, and this high strength or this tendon that I am considering this Fe 1860 grade high tension wire. The material properties are like that. So if you consider the material property of it, see its minimum yield strength is guaranteed at 1689. Can you see this figure? 1689, and the
Yes,
minimum
sir.
tensile strength is 1860. So with this grade of this material, these are all in MPa, that is Newton per mm square. I am now considering this uh, this particular data for material. So I have got material data. The second data I need is the section itself. So I need to consider the beam as such. So I have got this PT beam 400 by 900. So I am defining this 400 by 900 beam. So you can see this, I have selected this section 400 by 900. The grade of concrete that I have considered is M35. You can see that. So I am naming it as PT beam 400 by 900. So this is the size of the beam and so on. Okay. So I have defined the material. I have defined the section. I have also considered the kind of support that I am providing. So at these two ends, I have got at one end I have got a hinge support. So if you see this support, which I have indicated, all the three displacements, UX, UI, UZ are restrained. So I am restraining one end completely as far as the linear displacements are concerned. The rotation is permitted because I have got a simply supported beam. Similarly, at the other end, if you see, I have only considered UI and UZ as restraint. Now, UZ is an upward direction and UI is a horizontal direction in the direction perpendicular to the beam. So, we will now consider that for this beam, the displacement in X direction is permitted. This is a roller support for displacement in X direction. But vertical displacement is restrained, and horizontal in this direction also, that is XY plane. If you consider the if you consider this XZ direction, which is shown in the arrows over here, this Z direction is Y direction is in the horizontal plane. So my XY plane is horizontal. Okay, as simple as that. Now that is as far as my material data and the member data is concerned. For my data for the tendon, now you can see that for this tendon, now we have got this profile to be defined in this case. I have already defined the profile. So here you can see that the nomenclature is shown at the right hand corner over here. So at the center, whatever is the distance, that is indicated as ZC, and that you have to define as minus 800. Now I have got this beam whose depth is 900. The datum is at the top. You can see the red line. Can you see the red line?
Yes, sir.
yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now from this, yes. Yeah, you can see the red line. Okay. Now from this line, I am measuring downward the distance, so which I have defined as minus 800. You can see that 800. Okay. So at the center, this node that I have considered is 800 mm from the top, and it has got therefore from the bottom a distance equal to 100 mm. Now that is the center of that cable. Okay. So this is the center of the cable that I have considered. At the left support and at the right support, I have considered the cable to be positioned at the center because I have got total depth of 900 millimeter. Out of that, I am considering from top a distance of 450 at the left support and 450 at the right support. So I need to consider this distance 450, this distance 450. In between, I have taken a parabola. You can see this curve as parabola. You can see that this curve, there are various options which I think right now are not highlighted because I have got a run model, but there are several curves indicated, but parabola is most popular, so we have taken parabola as a curve, and accordingly you can consider the cable profile as parabola with these coordinates at the end points, 450 from top left and right support and 800 from top at the midspan. Okay. Now you consider this as the cable profile. As far as the definition of the cable is concerned, you need to consider over here, if you see this tendon section. Now this tendon section you have to define. So I have considered this tendon of 12.7 mm diameter, and I have considered for this the strand area as 600 mm square. Now if you see this 12.7 single strand, its area is approximately equal to 100 square millimeter. To be exact, it is about 98 point something, but we will take it as 100. I have taken 6 strands per cable, and I have taken 2 such cables. In that case, what area I am providing is 2 into 600. So in all, I have provided 12 cables, but the definition is given in this way, that individual cable I have taken as 600, but there is no cable of area 600. It is 6 cables, which I am calling it as one single cable of area 600 mm square, and I am providing 2 such cables over here. So if you see this particular cable that I have considered, so you can see at the right hand end over here, can you see this arrow? Okay, the number of strands I have taken is 2. Now individual strand I have taken as of area 600, which is equivalent to 6 cables of 12.7 diameter. Okay. Now this is the way I have considered the data. I have considered now the complete material data, that I have got the material concrete, I have got non-PT steel, I have got PT steel, I have got tendon with its profile, I have got support conditions. Now the last thing I require is the load applied on the given member. So on this member, I have applied the load. If you consider this load, so I have considered this load as 15 kilonewton per meter in addition to self weight. I think earlier I have indicated 25, but actually I have applied 15 kilonewton per meter, or was it 15 only? Okay. Now I have taken the load, superimposed load on it as 15 kilonewton, that is taken as live load. The self-weight of the beam is already part of the load itself. So I have got self-weight as a dead load, and I have got this live load applied on it. Okay, now the complete load is applied on the given structure, and now we say that the run command is given for ETABS. The entire process is complete, and now we can see the results of the analysis in our presentation. Okay, so this is the way we prepare the data, that is the material data, the section data, the cable data, then we have got the load data, and lastly the support data. With all this done, the results are now obtained, and now we can see that with this particular analysis done. Okay, now I am considering this analysis. Now we see that we have got in all 3 actions over there. One is the self-weight, which is going to cause some internal forces, and we have got the live load, and third is your pre-stress tendon. Okay, now with these 3 loads, now let us see how we consider the behavior of the beam in this particular case. Okay, now I have got the self-weight bending moment. So I have got the self-weight. There are different loading cases. I think I just forgot to tell you. Okay, now with this particular case for this beam, now we have got the loading cases. So we have got the loading case as dead load, live load as such. Now this modal load, we are not much interested in that, because our objective is to only consider the analysis for dead load only, dead load plus live load. Then we have got this pre-stress force. So we say that there are 3 different cases which are built into the ETAB itself: PT transfer, PT final, and PT final plus the hyperstatic forces. Okay. Now this PT transfer is the state at which you have got the beam with only its own weight. So you have got the dead weight, and then you are applying the pre-stressed concrete, because live load will come later on when the beam is placed in operation and then some load is placed on it. At that stage, the live load will be applied, but initially it has got only the self weight. So for self weight only, you need to consider PT transfer, because the losses are yet to occur. So we have got PT, that is pre-stressing force, at the instant when you stress the cable and lock it. At that stage, whatever is the force transferred to concrete, now that is called as PT transfer. So this is devoid of, that is, it is independent of the losses taking place. Losses will occur later on. The elastic shortening will occur, the relaxation will occur, the creep will occur. So all these losses will occur later on. But at the initial stage, when you are just transferring the stress force, at that time you have got full force applied except the slip loss, because after slip occurs, the cable gets locked into. So accordingly, we say that we have got this PT transfer. The second one is PT final. After all the losses have occurred, then you have got the PT final. That is your friction loss and creep and shrinkage, elastic shortening, all of this put together will finally give you PT final. And these hyperstatic forces, because of the internal indeterminacy in the given structure, that you have got there is non-PT steel, that also gets compressed. So all these internal phenomenon, they occur simultaneously, and there is a lot of redundancy. So some additional forces are developed which are internally calculated by the software itself, which by manual calculation it is very difficult to calculate hyperstatic forces. We will not go into the details of that, but we will only say that okay, there are certain phenomena which occur due to displacements and so on and so forth. So all these are accounted for in hyperstatic forces. So all these cases are considered, and your loading combinations are again provided by the software itself. So we have got the first loading case. If you see its loading combination, it is dead load. The first case that we are now considering. Okay, now this second loading case that I have got is 1 times dead load plus 1 times PT final and so on. The first one is dead load plus PT at transfer. The second one is PT at final. The third one and so on and so forth. So all these loading cases are generated by the software itself. Now what we have considered in this case is dead load plus PT final, and second is dead plus live plus PT final. So these two cases are considered in our presentation and so on. So I will now show you the different primary cases which we have considered from the given loading cases. One is your self-weight, that is your dead load. So that is the bending moment due to 15 kilonewton is the live load, but self-weight correspond to 400 by 900 cross section. So with density of concrete of about 25 kilonewton per cubic meter, you will get some self-weight. Okay, that is the moment due to the self-weight. Then we have got moment due to live load. Okay, now moment due to live load due to that 15 kilonewton and 15 meter is the span. So accordingly, you are able to get this moment due to live load. And due to prestress force, as you have seen the cable profile, there is maximum eccentricity at the center because your CG is at 450 from the top. The cable is 800 millimeter from the top. So there is an eccentricity of about 350 millimeters for the cable at the midspan. So at the midspan, there is maximum eccentricity, so maximum moment. As you go toward the support, no eccentricity, so there is zero moment. So this is the bending moment diagram that you get due to the pre-stressing force in the cable. Okay. Now once you combine the two, okay, now we have got these two combinations. One is dead plus PT final. So we have got final pre-stressing force with all the losses, and there is dead load, which is including of the self-weight. So it is self-weight plus PT final. Then we see that okay, there is a negative moment at the center because as you see over here, this moment due to pre-stress, which is about 507 kilonewton meter, the moment due to dead load is 238. So we see that there is some net negative moment developed due to the self-weight and the pre-stressing force. So that is the effect that you can see over here. So this effect is the initial stage when the live load is not there. So this is the point which I wanted to stress, that if you inadvertently say that okay, let me apply more force, then there may be a dangerous situation that your load is very small and pre-stressing force is very large. So a very large negative moment may be applied and then maybe develop, and then structure may be in danger of cracking and so on. While the second loading combination that we get is dead plus live plus PT final. So we are combining the three, all the three, that is this 236, then I got this 421, and this is 507 or 597 or 507 subtracted from that. The result of that is there is some positive moment left at the midspan. So we now see that bending moment under combined load is later on used or checked whether the beam is safe or not and so on. Once you know the bending moment, then you can always calculate the stress at the top, stress at the bottom, and thereby you will be able to get this kind of stress variation. So I have got this stress distribution span wise for top fiber. So if you see for top fiber, there is this minus sign that you can see over here, -9. Now that is the compression in top fiber at the midspan, while at the support there is -4, because there is a uniform applied force over there that you have considered for these cables. So at the end there is no eccentricity, but there is uniform compression. So there is a uniform compression of -4 at the support, and at the center the compression is maximum at the top fiber, which is due to the bending moment as well as the direct compression. So I am getting this top fiber in compression all along. If you consider the bottom fiber stresses, then you will see that bottom fiber stress also at the support, it is uniform compression right from top to bottom, it is -4. While if you go near the midspan, then we see that there is a positive moment developed. So at the bottom, the tensile stresses will be developed. Though of course you have got uniform compression 4, but the bending stress is more than that. So there is a 1 Newton per mm square of tensile stress developed at the bottom. Now you can conclude easily that the maximum compressive stress that you are getting is about 9 for M35 grade concrete, which is permissible. Normally about 0.35 of grade of concrete. So if it is M35, and if your compressive stress you want to consider, then normally you will be able to go up to 10 Newton per mm square, because 0.35 into zero point 0.3 of FCK, you will be able to restrict the compressive stress. So that will be limited to 10 or 11, and you are within limit. Same thing happens for tensile stresses. Now tensile stress is generally limited in such cases to about 10% of FCK, that is 0.1 FCK. So you will be able to go up to 3.5 Newton per mm square, while actual stress is 1. So you can say that your beam has got satisfactory parameters, and this beam can be designed with prestressed cables, 12 cables you will have to use, and so on and so forth. So this is the way we consider the design of the beam. There is additional design to be done, that is longitudinal reinforcement at top and bottom, because there is some tensile force developed. Though concrete is able to withstand that, we don't want to rely on that and want to still provide for balance moment, because we have seen in the earlier example that there is some moment which is at the midspan. So this moment developed at the midspan is to be taken care of. So we are providing this longitudinal reinforcement at top and bottom. Of course, at top there is no tensile stress at all, so no reinforcement is required. Some nominal steel can be provided. While as far as the bottom fibers are concerned, you will be able to get this additional reinforcement at the bottom, and so on and so forth. While for shear reinforcement, that shear force is due to the applied load and self weight. So you need to provide shear reinforcement in terms of the stirrups that you are providing. So it is square millimeter per meter. So you can decide the diameter, number of legs, and the spacing of the stirrups can be worked out by using this simple concept, which you otherwise use for normal RCC beam. So the shear design is as per normal RCC beam, and for bending moment design, you have got the combined action. Some part of the moment is taken by non-PT steel, and some part is primarily resisted by the pre-stressing cables that you have. Now the same thing we shall repeat. I think, do we have time for that? Okay. I think we have got still 10 minutes, so we should be able to cover that. So we shall now go for PT slab design using again the same software. So I have considered this 8 meters by 8 meters span. Okay, there are 4 columns at the corners, slightly inside the end one over there. And for this slab, I have considered the thickness as 200 millimeter. These columns are 300 by 300, and these 4 corners, and they are 3 meter in height, and so on. That is only a support that is provided for the given slab over here. So for this slab, therefore, now we try to use ETABS software for its design. It is designed for a SIDL, that is, you can say floor finish and so on, to the extent of 1 kilonewton per square meter, and live load that we are considering is 4 kilonewton per square meter. So we are considering this data for load. Then the strands that we have considered, now this blue line that you see, they are in fact strands, two numbers of strand at 1 meter center to center. So I have provided these strands, this sheathing that is required. And so this is provided at every 1 meter spacing, and inside each we have got two strands. So totally we have got 18 strands in X direction and 18 strands in the Y direction. Okay. So we have got this basic data decided. Now let us see the performance of this slab. See, right now you have got some data which includes strand. If later on you realize that, oh, these strands are too many or these strands are less because the stresses are exceeding the limit, then you will have to go back, change the number of strands or change the thickness, whatever that is possible, and accordingly you can revise the design and go ahead with that. Okay. Now, for considering the profile of the strand on the same lines, we have got this 200 thick slab. So for this 200 thick slab, as you can see over here, that we have got this initial straight portion, then we have got this parabolic profile, and then we have got the straight profile at the end. Now this entire cable is divided into three segments. Initial part is a straight segment, then we have got reverse parabola. Now this parabola is called as reverse parabola. It goes in this fashion and again is flattened out at the end. So there is a reverse parabola in the initial portion, in the central portion, and a linear portion at the end on the right side. Okay. Now if you see these parameters which are defined over here, then you can see over here that the strand is placed at the end at 100 mm from the bottom. Its total thickness is 200 mm. So I have taken it 100 mm above, and for the center it is taken as 25 mm above the center, because the strand is very flat and it can be placed, its center of its CG is placed at 25 mm from the bottom, and thereby we have got this complete profile defined over here. So this way we consider the profile, the strand as such. And as far as the slab is concerned, as you know that for flat slab of this type, you have to consider the behavior in terms of strips, even in normal design by slab. So we have got this column strip, we have got another column strip in X direction, then we have got middle strip over here. So we have got three strips in X direction, two column strips and one middle strip. Similarly, we have got three strips in Y direction, two column strips and one middle strip. Okay, so we have got this data ready. We have to take the strips, and then accordingly for each strip the results will be available in terms of the reinforcement required or in terms of the stresses and so on and so forth. Okay, now that is as far as the data is concerned. If you consider the ETABS software as such, then we will say that we have got these columns already part of the data. So we have got this column which is 300 by 300, that is defined in the definition, that is your section properties. So we have got this column 1. So we have got this concrete column 1 which is 300 by 300 in cross section. So this is 300 by 300 and some nominal reinforcement. The grade of concrete is M35 and so on. So we say that, okay, this is the member that I have considered as far as the column is concerned. Similarly, I have defined the slab. So for slab, I have taken this slab which is 200 thick. You can have a look at that. So this slab is taken as 200 mm thick, and it is taken as a thin shell, and accordingly the behavior will be adjusted with axial compression and so on. As far as the strands are concerned, again on the same lines you are defining the strands. So you have a tendon section. So you have got this tendon section with area, as I told you that this 12.7 diac tendon has got an area of about 99 square millimeter. So I have taken this, and two tendons are taken in each sheathing at a spacing of 1 meter. The load we have already seen, the kind of load that we have applied, and then the analysis is done. As far as the loading cases are concerned, we have got again on the same lines the dead load, the live load, then we have got PT final, PT transfer, and PT final with hyperstatic stresses calculated. And we have got the load combinations on the same line. So we have got all these default load combinations which are internally developed by ETAB itself. So this DSLB N1 considers dead load plus PT final, and N2 considers dead load plus live load plus 1 times PT final. Okay. So these are the two primary loading combinations which we have considered in our presentation, and so on. So we have got this data ready. This data ready, and then we see that after the analysis is done, okay, once the analysis is done, we are able to get the moments in the strips. So we have got this middle strip in x direction and y direction. So we have got this moment due to dead load, that is self weight of the slab itself. So it is 114 kilonewton meter moment, and in both direction it is the same moment, while the column strip has got different moment and so on. So we have got these x and y direction moments due to dead load. The moment due to PT final is also indicated over here as per the cable profile. The midspan will have maximum eccentricity. At the end, we have got very small moment, while at the end where we have got these restraint provided over here, there we see that there is a small amount of negative moment developed at the end because of the profile of the cable and so on. Now the bending moment due to dead load plus live load plus PT is now considered over here. So we have got all the three loads put together. So there is some negative moment developed at this end, positive moment developed due to dead load plus live load minus PT because of its negative sign and so on. Now, once the moments are developed, the reinforcement is internally worked out. So we have got this reinforcement in the middle strip over here. It is about 504 square millimeter in the entire middle strip. The middle strip is 4 meter wide. So in 4 meter wide, you have to provide 504 square of area. While the end strip, that is column strip, which has got 721 square millimeter area of steel, the width is only 2 meter, and here some negative reinforcement is required about 780 square because of the fixity provided by the column and so. So in all the directions, now we have got the reinforcement worked out and the data is ready. I think so. Okay, now that is as far as the you can say the bending moments are concerned. Now we consider the just a minute. Sorry. Okay, I think. Okay. Now these are the stresses which are developed in the slab. So this is stress S11, which is the stress in X direction. You can see that the entire chart has got color coding. So there is a stress varying from this red color, the mild red color that you see. It has got a stress of about 12 or between 8 to 12. Now that is the kind of stress that you are getting at these points. Similarly, you are getting stress near the column, which is reasonably high. Locally, of course, very high stresses are developed over here and so on. Similarly, you can consider the stress S22, that is in Y direction. The stress in Y direction again is obtained in this fashion, and you are able to get the stresses in that range. So the software calculates the stresses. You have to check whether the stresses are within limit or not, and so on and so forth. So you are able to get these stresses in a tabular form also. If you see this over here, okay. Now, okay. Now you are able to see these stresses if you in the column strip as well as in the middle strip. Okay. So this design. Okay. This. I think I will just show you these stresses. Just a minute. Give me 1 minute. I will just rerun it and then show you the stresses. I think the time is almost up, but I think in 2-3 minutes we should be able to.
Sorry, you can take a 5 minutes, 5-10 minutes.
Okay, okay. Yeah, yeah. Yeah, so I'm just executing the program again, get the results and show you the kind of data that is available in the output. Okay. So this complete data is available. Now you can go for design. So you can concrete slab design. You can use this option. You are able to design it. Okay. So it designs on the basis of strip as well as finite element based design. Both things are available, and it develops. It gives you relevant information. And as far as the tabulated results are concerned, you can see over here this concrete slab design output. If you see that, so you can see for each of the strip that you are considering, for each of the span, the moment is there with you. That is the bending moment is available. Then you have got the area of reinforcement available, and so on and so forth. So the entire data is available in tabulated form. Further, you can see that the stresses are also available in the design table itself. So you can see these analysis results. Okay, your strip forces is one thing. You need to consider the now this flexural stress, the bending stress that you are getting. Okay. Now you can see on the same lines the stresses which are developed at different locations. So you can see over here the compressive stress at top, compressive stress at top, then the stress at bottom. So the entire data is available for different strips that you are considering in x direction as well as in y direction. At different points all along the length, you will be able to consider the stress at top, the stress at bottom, and so on and so forth. If you consider, for example, this option, the slab option for this case, so you are able to get these stresses, resultant stresses. You can check the shell stresses, and if you consider now these stresses to be seen over here, then you can see these stresses directly, the diagram which I have shown you. So you are able to see these different stresses on any element. Once you click it, then you will be able to check, see the color very carefully and see the stresses at different location. As you move the cursor, you can see that the value of stress is shown below this, that is about 13.55 MPa, and so on and so forth. So you can see that for different loading cases, you will be able to see the stresses at different points. For all these elements, you are able to get the stresses and so on. So this will be a very simple task for you. You generate the model by using simple commands of ETABS software. For that, you need to define the material, you define the sections for slab or beam, you define the support conditions, then you define the reinforcement that you are going to use, consider the loads, and for prestressed concrete, there is only one change, and that is you are going to use the strands. So for that purpose, you need to define the section properties in strand. Okay, so you have got for strand these definition to be considered for strand, where you are considering area of strand depending on the diameter that you are selecting. So once you select for a given diameter the uh, uh, data for the strand, in that case the entire operation is ready to be executed. So you can now see that for this particular structure, you need to have very simple concepts. You need to have the problem before you, which is there with you. you need to consider only one additional thing in addition to what you were doing for reinforced concrete, and that is define the tendon section, the number of tendons and so on. That can be anything. Later on you can always revise if it is not satisfactory, and you have to define the profile. So once you draw the profile, you go back to that menu and then define carefully the profile, and then multiple tendons can be drawn in that particular case, and then you are able to directly consider the solution of the problem in this case. If the results are satisfactory, then you are okay. If results are not satisfactory, you go back to revising slab thickness or revising tendon number or sizes and so on, and then you are ready with final design. I think with this we come to the conclusion of the entire presentation, and I am glad that you have given me a patient hearing. So with this last sentence, I am now taking this lecture as concluded and say that thank you for your patient hearing. Thanks all.
Okay, thank you, sir.
Thank you.
And chalo, thank you very much, sir. Best wishes. And sir's granddaughter is here in the photo.
Ah, yeah. So that big thank you, which only I want.
Yeah. Yes.
Okay.
Okay, sir. Thank you very much, sir. And I hope students have enjoyed it.
Yeah, we can have their feedback later on. Yes.
Yeah. And later on, we will discuss, sir, on some project topics.
Yeah. I told you about that.
Yeah.
We need to take it further, I think. Yes.
Yeah. So, okay. Thank you, guys. You can join other lectures, and I'm ending the class. Sir, thank you very much. We can see
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
You are
sir.
most
Thank you, sir.
welcome. Most welcome.
Thank you, sir.